Nuclear power plants can provide a large amount of energy with a small amount of fuel, but they're good until they're not, which makes most people nervous. Today's lesson is on another type of non-renewable energy, harvesting nuclear energy. So, nucleotides are the formulas used in nuclear reactions. The common nucleotides are on page 8 of your data booklet. So this will give you the mass as well as the formula of different nucleotides. The top number is the mass number, which is going to be the protons plus the neutrons, which can change if neutrons are added or removed, which would form different isotopes. The bottom number is the atomic number and does not change. So the bottom number is what's going to identify which element that we are dealing with. So here's the mass of different selected nucleotides from your chart. So we can see that we have 2 different berylliums in the second from the top, depending on their proton and neutron, their mass number, but their atomic number 4 stays the same. And we have a few different hydrogens, which we're going to use very often, and uranium, which we'll also use quite often in nuclear reactions. So we have 3 different types of nuclear energy. We have nuclear fusion, which is the joining of 2 small nuclei, which occurs in stars and tokamaks. So this would be like taking deuterium and tritium and creating helium and a neutron. Nuclear fission, which is the splitting of one large nuclei into smaller particles, occurs in CANDU reactors. So this is how we create nuclear energy in Canada. So for example, we would take uranium and a neutron and then produce barium-141, krypton-92, and 3 other neutrons. So unfortunately, radioactive decay is the production of a particle from a large nuclei. And so this occurs inside the Earth over long periods of time. But in nuclear reactions, we have to deal with that nuclear particles. So alpha decay produces alpha particles, beta decay produces beta particles, and gamma decay produces gamma particles. And the weights of those, as well as the symbols of those, are in your data booklet. So when we look at nuclear fusion, this is the process by which nuclei of atoms are joined together. And so fuel is in small elements like hydrogen, and larger new elements are produced. This produces large amounts of energy, so like 10 to the power of 8 kilojoules per mole, and it occurs in stars such as the sun. And right now, this would be a very nice renewable source of electricity and energy for Earth, but we have a difficulty controlling the amounts of energy that are produced. So we see at the end that Y symbol is the gamma decay that is produced. That's the gamma decay that is produced. So nuclear fusion is an area where there's lots of research in right now to use to produce energy for humans. So nuclear fission is the process by which the nuclei of atoms are split. So we take a large unstable element like uranium and produce new smaller elements, and still large amounts of energy, so 10 to the power of 10 kilojoules per mole. And this occurs in reactors such as the Canadian deuterium uranium reactor, where the formula or the equation that represents the reaction is uranium-235 plus 1 neutron produces barium-141, krypton-92, 3 neutrons, and gamma radiation. So this new neutron causes 3 new fissions because we have 3 neutrons in the reactant side. That can then start 3 new decompositions. So these 3 neutrons that are now products can go back and start 3 new reactions in a chain reaction. So radioactive decay is the process by which elements naturally decay to produce other particles, and this naturally occurs inside the Earth, creating geothermal energy. So we have 3 different types of decay. Alpha decay makes positively charged alpha particles, which we identify as 4 helium to negative. And beta decay makes beta particles or electrons, which is 1 negative 1 e. And gamma decay produces gamma radiation. So here are those 3 subatomic particles. We have alpha particles, which is a helium nucleus or the alpha symbol, beta particles, which is our electron or a beta symbol, and then gamma radiation, which has no mass and is represented by a Y. So here we have alpha decay, which is an unstable nucleus, can decay into alpha particles, beta decay, where an unstable nucleus will decompose into a more stable nucleus and an electron, and then gamma decay, which is a photon, where it doesn't change the mass of any objects. Now, to protect ourselves against the decay from nuclear reactions, the different types of decay have different types of necessary shielding. So for alpha decay, we can protect ourselves with a sheet of paper because it's very low energy. For beta decay, which has a medium level of energy, we need to protect ourselves with things like thin sheets of metal or thick sheets of wood. Now, for gamma decay, which produces very high energy in particles, we need to have a layer of lead or very heavy metals or a very thick layer of concrete. So when you think about like those nuclear fallout bunkers, they would be protecting from gamma decay. Now, to measure nuclear radiation, we use a device called a Geiger counter, and it can measure the amount of beta, alpha, or gamma radiation in an area to see whether there's any nuclear waste from a fallout, or if there's been any. We see them in movies when people have stolen something from a nuclear power plant and they're trying to find them in people's hotel rooms. So I'll use the Geiger counter to go find the nuclear radiation. So we can also balance nuclear reactions because with the mass and atomic number. So we have to determine the type of reaction that is occurring. Is it a fusion reaction, a fission reaction, alpha decay, or beta decay? We want to write down the reactants that we start with. And on page 8 of your data booklet, you can use the atomic number. And you can also find the atomic number from your periodic table. The mass, the top number will be given to you. So radium 226 has a mass number of 226, but you want to find the atomic number of radium from your data booklet. So write down the different products, whether it's alpha decay, beta decay, gamma decay, fusion, or fission, and then determine the unknown product from the atomic numbers given. So the reactants' atomic numbers and the product's atomic numbers all should be equal on the left side and the right side of the equation. So they should be balanced, left side versus right side. So this is very similar to balancing a chemical reaction, except we're using atomic numbers and atomic mass. So here we're going to start with uranium 235 to produce barium 141, krypton, and 3 neutrons. So we want to find out the unknown atomic mass numbers and atomic numbers. So when we look on our data booklet, uranium has an atomic number of 92, barium 56, and krypton 36. And we just find these on our periodic tables. Then to find our left side versus our right side, we're going to take the mass number on our reactant side, which is 235 plus 1, subtract our product side, which is 141 and 3 neutrons, 1, and we're left with 92. So that is going to be the atomic mass number of the krypton is going to be 92. So it's, again, just simple. Once we find the atomic number of our elements, we find our one unknown atomic mass with a simple left side versus right side of the equation. Okay, so now deuterium and tritium fuse into helium-4. So this is a fusion reaction. So we can look at our periodic table to find the atomic numbers of these different compounds. So we have helium and a neutron because that is what is 1, 0. N is what is going to be A, B, and C because that's what's produced in a fusion reaction. And then to make helium, D and T are both going to be hydrogen ions. Oh, this one has to be 3. because we have the weight of 4 plus the weight of 1. So we have to have 5 on the right and 5 on the left. So this is what D and T are respectively. And we know that, and if we looked at our fusion reaction in our data booklet, it tells us that helium will be made from 2 hydrogen atoms. Okay, so if we have radium-226 undergoes alpha decay, we're going to identify our atomic numbers from our data booklet. A is going to be equal to 88. C is going to be 88 minus 2 because there's going to be an atomic number of 2, an atomic mass of 2 on our hydrogen or helium. So here C is going to be 86. Now we have to identify B, which is going to be the mass on the reactant side minus the weight of the helium. So 226 minus 4, so it's 222. So we're going to go look for atomic number 86 on our periodic table, which is going to be radon. So all of the information that we have in our data booklet, we're going to use to solve these nuclear reactions. So again, left side equals right side. It's important to, again, look in your data booklet when it says alpha decay, what is produced? Helium. And then when we have our unknown element, we need to look in our periodic table to find the element with that atomic number. So now if phosphorus 34 undergoes beta decay means an electron is produced. Okay, so when we go through, I want to identify the atomic mass of B is going to be 34 because our left side of the equation of our reactants is 34. Our other atomic mass is 0, so B must also be 34. Then to find C, we take 15 on our reactant side. We subtract -1 from it because we have 1 electron, and then we get 16 as our bottom number on the element D. So now to look up element D, we go to our periodic table. Element D is 16, which is then going to be sulfur. So we can rewrite our equation as (3415) phosphorus produces 3416 sulfur plus 1 electron. So that would be our new equation. And if I go back to the previous example, we have 226 over 88 for radon produces 222, 86 Rn plus 4 over 2 helium. So that would be the completed example for alpha decay and beta decay. So when we're comparing the energy available from different fuel sources, if we needed to run Toronto for a year, we would need over 2 million tons of coal or 10 million barrels of oil, 150 tons of uranium fuel for nuclear fission, or 0.6 of a ton of fusion fuel, or 1 pickup truck. So we can see that fusion reactions would create the most energy, but like I said, we're having a difficult time researching how to control the heat that is created in a fusion reaction. When we look at different emission comparisons, carbon dioxide production from coal, natural gas, and oil is highest for coal. Sulfur dioxide emissions are highest from coal, as well as nitrous oxide emissions are highest from coal. Nitrous oxide emissions are 0 with natural gas, which is why we can often consider natural gas to be a clean heat source. So when we look at the energy production of different reactions, if we have a phase change reaction, so like we condense water. This is a change of up to 100 kilojoules. So it does produce some energy, but not very large amounts of energy. Now, a chemical reaction like combustion produces up to a 10,000 kilojoule energy change. So much more useful amount of energy is going to be released in these reactions. Nuclear fusion creates a energy change of up to 100 million kilojoules. This would be the forming of particles. A nuclear fission, or the breakdown of particles, creates more than 1 billion kilojoules. So more energy, but it also creates nuclear waste. So in nuclear reactions, because mass is lost, it's as those compounds are converted to energy, we can determine the amount of mass lost, and then we can determine the amount of energy that was created in an equation. So mass must be lost in kilograms, and c squared is going to be the speed of light. So 3 times 10 to the power of 8 meters per second. So to calculate the mass lost in nuclear energy, you're going to write a balanced nuclear equation using the nuclear chemistry chart on page 8 of your data booklet to find the masses of the reactants and the products. And we want to include the times 10 to the negative 3 because that's how actually small they are in kilograms. So add the masses of the reactants and the products, subtract the reactants from the products to find the mass lost. Then we substitute that value of mass into E equals mc squared and multiply by the speed of light to find energy released in joules. So here's our balanced nuclear reaction for the fission of uranium. So we have our mass of uranium at 234.9934 times 10 to the negative 3 kilograms, plus the mass of a neutron gives us a total mass of our reactants of 236.00207 times 10 to the negative 3. And we want to keep all those decimals in there. Now the mass of our products, so we have barium, krypton, as well as 3 neutrons, giving us a total mass of 235.81542 times 10 to the negative 3 kilograms. Now again, these are all found on your nuclear energy chart in your data booklet. So we want to take our mass lost is our products minus our reactants. Reactants minus products. So 236.0027, subtract 235.81542, and we have a total mass lost of our reactants of 0.18665 times 10 to the 3 kilograms. Now we can put this into our E equals mc squared, so we multiply that by the speed of light. And again, we want to keep all of our decimal places. And we end up with a total mass energy of 1.68 times 10 to the 13 joules in the decomposition of 1 mole of uranium. So a massive amount of energy is produced. Unfortunately, nuclear waste does create, nuclear energy formation does create nuclear waste. So the CANDU reactor uses deuterium and uranium. So we use this to create heat, to boil water, to spin a turbine, to spin a generator, to create electricity. So similar to coal-fired power plants, we just have a different source of heat. So we have nuclear reactors in different parts of the country. Most of them are in the Ontario, Quebec populated core. We have some in Atlantic Canada, 1 in Alberta, and 2 in Saskatchewan. In a CANDU reactor, our fuel is uranium-235 in fuel bundles that can be removed when they're used up. Our moderator is heavy water, which slows the neutrons to sustain the reaction. And the hydrogens in this heavy water are going to be deuterium. We also have control rods made of cadmium to move in to slow the neutrons in the reaction rate. So we want to control the rate of reaction so we don't have a nuclear meltdown. And then that coolant is going to be heavy water. We shield the outside of our nuclear reaction with carbon, steel, concrete, and water. So we would have a fuel loading machine on the right-hand side, which we then put into our reactor, which we're controlling with heavy water and cadmium rods, so our reaction doesn't go too fast. Then as we increase the temperature of that water, it produces steam, which is then going to spin a turbine, spin a generator, and produce electricity. Then at the end, that steam is going to be cooled by circulating water, and water is going to go back into the steam generator. So the reactor and the heat that are produced is kept separate from the water. So the only thing that typically gets into the water is heat. So again, in the CANDU reactor, we have an atomic reaction that makes heat to make steam, which turns a turbine, which spins the generator, which produces electricity. So similar to a coal-fired power plant, but just a different source of chemical energy. And into the CANDU reactor, it's one of the safest because the neutrons are controlled from preventing chain reactions. So the fuel bundles contain limited amounts of uranium. And what we do with our nuclear waste is we store it deep underground in the granite of the Canadian Shield. So this is our current plan, is to just bury the nuclear waste. So there is lots of research on fusion, which is the formation of larger atomic particles from smaller ones. So currently, there's valuable forms of energy on Earth because of a small nuclear fusion would be a valuable form of energy because a small amount of fuel releases a lot of energy. And the very big perk is there's little waste or radiation produced. But we're unable to control the energy released, which occurs at high temperature. So at this time, it would melt the current reactors that we have. So there's tokamak projects, an international one, a European one, an American one, and a Japanese one, and one in the former USSR. So when we look at the temperatures, we see that they are in the billions of Kelvin. So they're incredibly large. So these valuable forms of energy, again, are produced with little waste or radiation. So this is images of the Joint European tokamak with a magnetic plasma confinement. So again, we're going to try and control that heat. This is the International Thermonuclear Experimental Reactor. And in Canada, we have a tokamak in Quebec, as well as the University of Saskatchewan. And these are all places that we're studying fusion reactions to have a sustainable and non-nuclear waste producing form of energy. Hope you enjoyed today's lesson on harvesting nuclear energy. See you next time.